Hello, my name is Mingshen Sun. I'm from Baidu. And today I will present our recent progress on verifying confidential computing platform. First, let's get started with a very interesting example. Get started with two coffee instances. Have you ever experienced spilling out coffee? Have you worried about cleaning overnight coffee cups? Do you want a cup which never spill out coffee and never bother cleaning? Definitely yes, right? This is a problem our confidential computing community are trying hard to solve. Let me explain this to you in details. Enclave provides a trusted execution environment to hold users' privacy, just like coffee in the cup. We don't want to see privacy leakage while executing and privacy left over after the execution. Similar concept can also be seen in data privacy regulations like GDPR. It declares that users have rights to ask for data erasure, and the service providers have obligation to erase personal data without undue delay. Although many security primitives aim to prevent these incidents, they still fail to guarantee the incidents are eliminated provably. So TE claims three main security primitives. The first one, attestation. It guarantees identity of enclave code to any user, ensure that only expected code can be executed. The second one is isolation. It prevents outside attacker from stealing secrets in the enclave. The third one is encryption. It protects confidentiality and integrity of the data. However, we think this is not enough. Attestation cannot prove the trustworthiness of the code. Therefore, attested code may still leak secrets. In addition, TE isolation ignores internal threats, which may also lead to data leakage. The last one, the confidentiality, the encryption, the potential incomplete encryption and cleaning can still result in privacy leftover, which might be stolen by other parties. So TE does not guarantee no data leakage and secrets withhold. So this is why we are calling for a stronger privacy protection principle. We call it proof of being forgotten. So proof of being forgotten is a principle which regulates the code dealing with secrets is verified so that secrets are completely consumed and not revealed to any unauthorized party. So in short, proof of being forgotten ensures no privacy leakage and no privacy residue. Of course, not any arbitrary code can be proved with a no leakage and no residue property. We need to carefully design the enclave services to achieve this goal. To understand the proof of being forgotten in detail, we separate it into two aspects, design and implementation. We propose design with formalization, modeling, and prove it with in compliance with proof of being forgotten. We then implement a real-world confidential computing platform with several technologies and verify it follows proof of being forgotten. So let's start from the design first. Let's talk about our design from top to down. We prove and verify the proof of being forgotten principle. We formally define an important concept, being forgotten for procedure. It consists of two predicates representing no leakage and no residue separately. Our goal is to have a design which can be proved with the being forgotten property. Therefore, we can have the following design. Due Due to the time limit, let me quickly go through some concepts in our design. A proof of being forgotten compliant design can be disassembled into three constraints. First, restricted represents that the execution should be in a restricted zone, which prevent write-out secrets. Second, end with encryption, which means that a task should terminate with the encryption. These two are derived from no leakage requirements. The third constraint, clean moved, which means safe cleaning and safe transfer after execution. This is for the no residue requirements. Then with the compliance of proof of being forgotten in mind, we can have a confidential computing platform designed for general purpose platform for general purpose workflow. So more specifically, we have formalized constraints like restricted and clean moved, and bring them up a step further into details constraint rules. For example, restricted can be defined as a conjunction of write-bounded and read-exclusive. Clean moved can be defined as zeroized and safe transferred. To make it more clear, later we will talk about two concrete examples of the two constraints. Write-bounded, which is a procedure can only write to a specific zone, and the safe transfer, which means the return value must be passed to the next procedure intactly and cannot be accessed by any other entities. For more details, we will publish a technical report later. You will see the details in that report. We also plan to establish a formal model to support our proof of being forgotten theoretically. We are writing a series of constraints in proof systems. Such a proof can be used by confidential computing service providers to convince their customers that if certain constraints are satisfied, proof of being forgotten is then guaranteed. To give you a sense of our design, let me demonstrate how our memory model satisfies the constraints. We have a zone in the design in enclave, which is exclusively used by a protected procedure. That is a lambda in the figure. With restrict write operation to the zone when the procedure is running. For example, procedure cannot explicitly write secret out of the zone, out of enclave, and any untrusted places. This satisfies no leakage requirements. We also enforce safe cleaning at the end of the procedure, where zeros are written to all memory locations in the zone other than the return value after the execution. This one satisfies no residue requirement. So due to the time limit, I just went through the design of our memory model with no leakage and no residue property. You can read more details in our later release technical report. Now, let's turn to implementation from the bottom up. Based on the design, we implement a proof of being forgotten compliant platform. There are several techniques are utilized. First, we use Rust to implement our system, and the Rust programming language provides memories and thread safety. In addition, the strong and sound Rust type system and Mirai, which is a Rust abstract interpreter, together help us to verify the platform. For example, Dataflow analysis helps to enforce secrets are exclusively accessed by authorized procedures. And the type system, ownership rules, and the zone allocator help us to zeroize and deallocate the secrets faithfully. So this these techniques help us to implement a real-world confidential computing platform. So to give you a concrete sense of our implementation, let us look at two examples. One is how we verify the node leakage property. This example demonstrates how we use abstract interpreter Mirai to detect a privacy breaching risk. We add tags for the protected assets, and when the input head tag is verified as a precondition in the safe log function. When the code tries to print a secret key in log, Mirai detects an unsatisfied precondition in line 39. You see the right figure. Whereas in line 41, developers try to log an unsensitive information. In this case, Mirai doesn't comply, which means the precondition is satisfied. This helps to detect the risk statically. This is the right bounded property I mentioned earlier for the no leakage requirement. Another example is to demonstrate the safe transferred property for our no residue requirement. We use Rust type system to enforce data flow and state transition. In this way, secrets can only flow in a certain path, but not unauthorized scopes. For example, protected assets is a type which holds sensitive data. It can only be used for computation when the input data is encrypted. Since we enforce the data transition in the type system, any violation will result in a compilation error statically. In this way, we can guarantee the safe transfer property. Combined with the serialization, we can ensure no residue requirement I mentioned earlier. These just two examples methods we use to implement this verified confidential computing platform. We will release more implementation details later. In summary, we propose a new principle, proof of being forgotten, defining no leakage and no residue requirements for a confidential computing platform. This platform is verified towards the constraint which derives no leakage and no residue, and finally lead to proof of being forgotten compliance platform. The previously mentioned techniques contribute to no leakage requirements, no residue requirement, or both. Therefore, the verified code of the platform can be remotely attested, and the user can then trust the platform. This is how we use proof of being forgotten to profitably secure the privacy on a confidential computing platform. So at last, let me summarize all the talk. We propose proof of being forgotten, a principle, regulates the code dealing with secrets, is verified so that secrets are completely concealed and not revealed to any unauthorized party. The two main requirements of proof of being forgotten is no leakage and no residue. We formally define the constraints to prove the requirements and also gives concrete design and implementations in compliance with the principle. At last, let me present our recent release product, P4 Clean Room, which is a privacy-preserving computational biology platform with a proof of being forgotten property. We have released this platform in the Azure Marketplace. For more details, you can visit p4cleanroom.com. Oh, thank you for your time. This is all about proof of being forgotten.